and FAD reduced to FADH2. And don't forget, there is a GDP generate GTP. So how many ATP generate? NAD reduced to NADH2. I always use 3 ATPs as calculate. Your textbook is 2.5 ATPs because it's consideration the oxygen phosphate ratio. But I will be using this older one, which is relatively easy. And FAD reduced to FADH2, how many ATP generate? Is 2 ATPs. And you guys say is 1.5 ATPs in new textbook. Same thing, consideration oxygen phosphate ratio. That's okay, as long as you keep consistent. So let's see. How many places, which is NAD reduced to NADH2? It's 1, 2, 3, 4. Therefore, it is 3 ATPs multiplied by 4 equals 12 ATPs. That is for NAD reduced to NADH2. We have FAD reduced to FADH2. How many ATPs generate? 2 ATPs. And don't forget, there is one GTP, and the GTP at this moment is equals ATP. So there is a 1 ATP generated. If you add up together, 15 ATPs. And do not forget, through here, there are 2 citric acid cycles. Therefore, what we do is this 15 ATPs multiplied by 2 equals 30 ATPs. So a complete citric acid cycle, including transition step, there is 30 ATPs generated. And how many generate? Through aerobic respiration from glycolysis, if it's part of the aerobic respiration, is 8 ATPs. So you add up together, 30 ATPs, add 8 ATPs, is 38 ATPs. Okay, what I'm talking about this is for bacteria. You learned in your biochemistry class, talk about human being, animals, it is 36 ATPs. And there is 2 ATPs is gone. Where are they? Because for bacteria, it's prokaryotes. This happened in cell membrane system. For eukaryotes, this happened in mitochondria. And the mitochondria, they need to pass in the mitochondrial membrane system. Like you go to a park, you need to pay the tickets of the gate. So that 2 ATPs is the ticket gate. That's why you have to minus 2 becomes 36 ATPs if it's eukaryotes. Okay, so 38 ATPs is for bacteria, prokaryotes, and this is, we can say it's for fungi because it's a eukaryotes, same as animals. Okay, so this is, we finished talk about this whole thing. And we also mentioned the substrate level phosphorylation. But then you have one more question. How come these kind of things generate ATP? They generate ATP through electron transport chain. Electron transport chain. The acronym ETC. This chain in bacteria, in the cell membrane system, in eukaryotes, it is in mitochondria. So we could draw a model for the electron transport chain. What it looks like? It is NADH2 goes to FADH2, then goes to FES, FMN, then go to coenzyme Q, and then go to cytochroma C, then go to cytochroma A, then they go to cytochroma A3, and finally is oxygen. And this is accompanied with electron transfer. This is the complex, electron transfer. And carry on the energy, okay? So, this comes out with a very simple theory. Y, based on the electron transfer, will generate ATP. In 1932, Peter Mitchell have a very important theory called chemoosmosis. What a theory is that? During the electron transfer from NAD to NAD to FAD to FES, FNN, all the way go to oxygen, there is something coupled with the proton moves out of the cell membrane. So they moves out, and they move out. And the more proton accumulated out of the cell membrane system. And this creates a potential energy called proton motive force, PMF. So more and more go there. Potential energy, from the physical standpoint, will transfer to kinetic energy. A very simple example. You have a ball right here. You have a car right here. This ball goes off. This car will start to move. This is equals mgh. That's a physics we talk about. Potential energy become kinetic energy. Same thing here. You have all these protons accumulated. It's a proton motive force. It will be activate ATPase. This will be activate ADP becomes ATP. And what he did is using bacteria as a model. At the same time, what he finds is the bacteria will do this stir, and that's a flagella rotation. So that's the story of oxidative phosphorylation. One of the theory is chemoosmosis, and this is got a Nobel Prize in 1964. A great British scientist, Peter Mitchell, mentioned about this. Now there's a remaining question. Why NAD reduced to NADH2 is 3 ATPs, and FAD reduced to FADH2 is only 2 ATPs? Why? This is people did some of the other reaction. We call it 2-half reaction. 2-half reaction, which means is an oxidation and reduction reaction coupled, use voltage value to measurement whether a chemical is a potential energy donor or potential electron donor or potential electron acceptor. What they find? They find this NADH2, the value is pretty much like a negative 1.5 V. This FADH2 is like a negative 0.8. And you go coenzyme Q, it's become positive started, because maybe 0.1. And the oxygen is very positive, is 0.8. So what you see, the voltage distance between NADH2 to oxygen is very large, is about 2.3 V difference. And the voltage difference between FAD and the oxygen is a little bit small. It's about 1.6 V. That's why here transfer to the energy, which is 2 ATPs, and here is 3 ATPs. Now obviously, your textbook, this is 1.5, and this is 2.5. So that's what the difference it is. Okay? So, basically from here, we finished talk about the biochemistry, the overview. So, the key points here is, we go over the glycolysis, coupled with citric acid, how we're going to calculate the ATPs. What is ATP? The structure of the ATP. And we also have alternative energy currency, GTP, CTP, and UTP, what the structure looks like. And why they generate ATP? We have substrate level phosphorylation and oxidative phosphorylation. And what's the mechanism behind that? This is rely on the voltage value, but this is rely on the phosphor transfer power, and this is rely on is a proton motive force. And those two are different theory. So you know, if you answer substrate level phosphorylation, you simply say it is not going through electron transport chain. You just pick something from the other side. That's not a correct answer. You can see it. Because we also could ask you, oh, why this is an oxidative phosphorylation? You can say because it's not going through phosphor transfer power. So that means not answer anything. You know what I'm saying? But certainly a lot of the people answer like that. A lot of the textbook even wrote like that. But I don't think so. It's correct. The correct answer is right here, and this is where I explain to you what it is. So here we're gonna have two sections of the warm-up. We finished talking about the chemicals and also the biochemistry. So next week, Tuesday, we will have first section talk about the water. That's moved to real food chemistry. And the second section, Thursday, we'll talk about some sorption, desorption, isotherm, talk about ice. And the following, we will have one section for Ian to show us some of the lab practical material. That will be the following week. Will be basically 2 weeks from today. Okay, so that's all the plan what we have.